So I will consider a square box, lambda on ZD. And you have to think at this box as a large one. So you have sides in this box. And you can think of these sides as lily pads, because I would put frogs in the box. I would put n frogs, and n will be a fraction of the box, of the volume of the box. And frogs can be in two states, either active or sleeping. Either active, or it will be A, or sleeping. So maybe this one is an active frog, and this one is a sleepy frog, and I have only two frogs on this picture. And an active frog can do two things. At rate 1, it jumps on a uniformly chosen neighboring site, lily pad. On a random neighbor. So this one can go here, here, or here. And it can also fall asleep. So this will happen at rate lambda. Okay, so this is for active frogs. And the sleepy one, they stay where they are. They don't move. Until activation. And when is activation? As soon as it is not isolated. So for example, if this one travels here, then here, then here, then it will wake up the frog sitting in that place. This is because it arrives on the lily pad, and jumping on the lily pad moves, and the sleeping one is awakened, and it starts moving as the first one. And both can, at some rate, lambda, going back to the sleepy state. So of course, in this situation, at the end of the day, everyone will be sleeping. Okay. This model, you can think it as a reaction diffusion model. So the diffusion part is that one, the fact that active frog are diffusing. So, the reaction part is the fact that you can turn A to S at rate lambda, and an A and an S react instantaneously by making 2A. And this model was introduced in 2009, I guess, I believe, by Dickman. One N. Voilà. And Sidoravicius. Okay. Before going to the motivation of this model, I mentioned that this exhibits phase transition in the infinite volume. This means that if you put the density mu on a line, there will be a critical value for which below this critical value you will have fixation. Frogs will eventually stop moving. Each frog will eventually stop. And above the critical value, they, with almost surely, they will, they can't sleep, but they will be awakened and walk again, and they will never reach finite sleep. Works forever. So this is infinite volume for the model that you can define on lambda equal to ZD, natural generalization of that. And there is a counterpart in finite volume that I will discuss today, which is that below mu c you have a fast fixation. And above mu c, you will have a metastable situation. On a finite box, of course, if you have mu which is smaller than 1, you will, at the end, have, everyone will be sleeping. But this will take a long time, typically an exponentially long time, exponential in the number of frogs you have in the box. So you have a metastable situation. What I mean by that is that so this is in a finite volume, and metastable situation. That means that starting from everyone active, the probability is that the fixation time. So this is fixation time. Is larger than e to some constant time n, n being the number of frogs. This is 1 minus small o of 1, starting from all active. Okay, let me say one word now on the motivation of this. This model was introduced to describe as a candidate for, as a candidate for explaining the appearance of critical systems without anyone tuning the parameter to put it in the critical phase. Because this kind of model can reach self-organized criticality as soon as you put open boundary on it. Now the motivation. It should exhibit self-organized criticality with open boundaries. This is a conjecture. What do I mean by that? How can I explain this? So assume that you have frogs that arrive at, you start from empty box, and frogs arrive at some small rate. So a frog is arriving, it works a bit, and at some time it falls asleep, and that's it. And then another one arrives, maybe it wakes up the other one. And open boundaries mean also that not only also they arrive, but when they reach the border, they can also jump out. And maybe you will lose some frog, but as long as you are below the critical density, you will absorb new entering frog. But as soon as the density goes above the critical one, there will be sustained activity that will put extra frog outside the box because they will reach the boundary and jump outside, so the density will decrease. So it increases up to mu c as long as you are below, and it decreases to mu c as long as you are above, so that you have a spontaneous evolution to your system to critical state. This is what is expected for this. Is it clear? Question? Yeah. Sorry? Mu c depends on lambda. This is a mu c of lambda. So, but what I said is expected to be true for each value of lambda. Yes?
And also independently how the frogs come in.
So for this to work, you have to have a slow rate for putting frogs inside, and they equilibrate, putting frogs outside, and then.
But does the self-organizing criticality depend on the rate in which we add frogs?
The what?
Does the self-organizing criticality, should it depend on at the rate?
No. For a low enough rate for adding frogs, it should work like this. Okay. But for this to work, for this to be relevant, the first thing you have to prove is that you have a non-trivial phase transition. So the question I want to address now is do we have a non-trivial phase transition? And the answer is yes. So what do I mean by non-trivial phase transition? First thing is that you expect your mu c to be non-zero. So mu c is positive. So this was proved by Rollin and Sidoravicius in 2012 for d equals to 1. And this was proved by Sidoravicius and Teixeira. There is another. Right? Okay. 5 years later for larger dimension. And of course, you will have no fixation if you have more frogs than lily pads, because you cannot fix one frog in each lily pad. So the other question is it true that mu c is smaller than 1? And the answer is yes also. So this was proved by Basu, Ganguly, Hoffman, and Ricci in 18 and 19 for the special case d equal to 1, and by Stauffer and Taggi in 18 and 19 for d larger than or equal to 3. So the only remaining case is d equals to 2, and this is what I claim now. So this is a theorem. Now mu c is smaller than 1 in all dimensions, and for all value of lambda. These papers were for first for small value on lambda, and then all lambda, small value on lambda, and then all lambda, and we did the same. Small value on the first, and then all lambda. Okay. So, what I described above about finite volume and infinite volume as two sides of the same coin, the way we proved that mu c is smaller than 1 for the infinite volume phase transition is by proving metastability for the finite volume, large volume system. So what we have to prove is that for fixed lambda, if we put enough throg, but still a density which is smaller than 1, they will take an exponential time to fall asleep, that it is indeed a metastable situation. This is the title of the talk. Okay, and usually, to prove in metastable situations that the system will need at least a long time to make the transition to stability. This is usually the easy part. In this case, it is not so easy for many reasons. One is that, as Inksu said, we don't have control in this non-reversible situation on the equilibrium measure. And another thing is that we are very far here from a slow, small noise perturbation of a deterministic system. It's completely different things. And I want to, so I have 12 minutes. Okay. So in this 12 minutes, I will explain two ideas of the proof. One is what can you do with this kind of model? We don't have control on equilibrium measure, on this kind of things. And the other one is how do we use the fact that even though we are only proving the fact that your system will take a very long time to go to equilibrium, we will be driven in the analysis by the fact that we have a short time scale for fast thermalization. So this is an essential feature of metastability. Okay, so before to do that, I have to make yes? Question? No. I have to stress one fundamental and usual property of this system, which is called the abelian property. The abelian property is like this. So I described the system as a system of frogs that make some things. One thing you can do is to attach the instruction to size instead of throg. What I mean by that is that assume that you have this side in d equals to 1. And on this side, you say first, for example, the frog that will sit here. Maybe I have to take my example. Will first move on the right, and then the next one that will visit that will move on the left, and then it can also fall asleep. Here, it first fall asleep, go right, left, left, right, sleep, right. Okay. So one way to build the system is to read the instruction at rate 1 plus lambda. At rate 1, you have to choose something, and at rate lambda, you have to fall asleep. So you will have one instruction at rate 1 plus lambda, and this has to be distributed according to the correct distribution. This should appear with probability lambda over 1 plus lambda, and this 1/2 of what is remaining. So if you start with, for example, an active frog here and an active frog here, so this one will first, if it's the first one to read the thing, it will first fall asleep. it will be awakened by that one. So you will have two active frogs here. And then one will move here and fall asleep. And the other one will move in this direction, in that direction, in that direction, and fall asleep, and that's it. And the natural way to decide who is reading what is decided by the clock of frogs, but abelianity says that whatever the order you move the frog, you will read the same instruction and in the same configuration. And read it in any order to get same result. So you can take back my example, change the order of reading instruction, you will get the same final configuration. Yes? In any dimension. The construction is the one I just gave. Okay, so two ideas to conclude the proof. I have no time to make the whole proof, but just two ideas. So first one is to reduce the dynamics to density 1 dynamics. Reduce to density 1. How do you do that? So I'm interested, I want to prove that the probability that I fix in a time exponential time constant time n, let's say n is mu times lambda, I want to prove that this is small. So I will sum on all the possible sites where the frog will end. So this is equal to the sum on all the subset A with size mu times lambda of the probability that my time, fixation time, is smaller than some constant time mu lambda. And you end in A. But this is smaller than the sum on that the maximum of all this probability times the number of terms I have. So it is lambda choose mu A in lambda, no, mu lambda, this is lambda here, times the maximum of all A of size mu lambda of the probability that you end up before the given time and n in A. And if you do that, what you can do is also to neglect all the instruction you have of sleeping outside A. Because if you know that you end in A, all this instruction of sleeping will eventually be read. So they will play no role. So you can also add here and ignore instruction, sleep instruction outside A. So when you do that, you can start with particles only in A, because they cannot sleep outside A. And in A, they have two kinds of instructions they can read. Either they sleep, or they made a cycle awaking all the sleeping particles around and turning back to their position. So doing that, you go from a system with two kinds of particles in any place with a system of density 1 with only two kinds of states, either sleeping or active. It's a bit like a contact process, except that you infect a longer cycle rather than only your neighbors. And this term, this is small for mu smaller than 1, large enough. And this one, this decrease for mu close to 1. Actually, for mu equals to 1, this is only 1. So this will be exponentially large, but this will be exponentially small. And for mu large enough, but still smaller than 1, you can prove that this is very small. This is the way we prove metastability in this case. And I have 1 or 2 minutes, or is it finished? 3, great. And the other ideas. Okay, so this we can prove for, I said that it is a density 1 system, but of course the geometry of A will play a role. What enter into the game here is the trace process on A, the cycle you can make on A. And this will be different depending on the density on the geometry of A. Controlling this is not obvious for some space A. But if you take a connected A, this is A. This is not so difficult to prove. I have no time to prove that. Difficulty later is to prove for more complex A. And this is where metastability enters into the game again. If you have two sets A which is B and C, one way to stabilize this is to first stabilize B and then stabilize C. But while you stabilize C, since you make loops, you can activate some particles, some frogs there. And it's possible that, that you completely activate B while stabilizing C. So the time, if you call TA the time to stabilize the whole things, it would be at least the time you need to stabilize B plus the time to stabilize C. But maybe you will have to recommend to start again if with a probability which is 1 minus epsilon B times 1 minus epsilon C, where epsilon B is the probability of not awaking completely the other part while stabilizing this one. And you can continue like this. You have to repeat this. This is a ping-pong rally. You continue the ping-pong as long as you didn't have completely reactivate the other one. Now, what is this kind of, what is this? So this is probability to fully activate C while stabilizing B. What is the probability to do that? Because we have a metastable system, the probability to avoid complete activation of the other one it can be done only on the very first transient, because otherwise you will reach to metastable equilibrium, and you know that you will have to wait a very long time, typically, you will make a very long time to stabilize and then make many loops, and with many loops you will activate the other one. So essentially, this probability is the probability to avoid things in the very first transient. And because you expect geometric time or exponential time as a distribution to make stabilization, this epsilon B and epsilon C should be of something like, so this is epsilon B plus epsilon C, and this should be something like TB plus TC divided by 1 over epsilon B plus 1 over epsilon C, sorry, TB. The fact that in the very first part you make your stabilization, and if you compute that, this is just the product of the two. So if you have an exponential time with a constant in the size of the things, when you get to the union, you get the product of the two, and you have the size of both. So this goes like TB times TC. And this is the way to go all the scales up. Of course, for proving that, we are inspired by a metastability feature, but it's not a proof. And the proof use things like the first trick when you couple with a different system for which you can neglect some things, and at the end you eventually prove that the mechanism is in place. That's the way we prove that in all dimensions, too many frogs cannot fall asleep. Thank you.